Up to this point, we have been either ignoring friction or assuming that it's negligible. Now, that's not a realistic assumption in many situations, and so in this chapter, what we're doing is we're looking at situations where we can assume that friction is acting. What we'll see is that's going to cause the motion of an object to behave differently than it did when there was no friction acting. Now, as you can see in the definition here, friction is the force that opposes the motion of an object that is either sliding or attempting to slide on a surface. And these two situations are going to come up in just a second, and that's what we're going to be discussing today. Now, in general, when we talk about friction, its symbol is a lowercase f. Its units are newtons because it's a force. And so there are two situations. The first is when the object is actually sliding along the surface. In this case, we describe that friction as kinetic friction, the force that opposes a sliding object. Its symbol is F sub k. And the nice thing about kinetic friction is it is constant. And so while friction may make situations more complex, having a constant force is still vital because it means it provides a constant acceleration, and a constant acceleration means that we can use the kinematic equations. Now, when we say that kinetic friction is constant, we mean it's constant depending on the object that we've selected as well as the surface. And so the kinetic friction really depends on the normal force, the object's composition, and the composition of the surface. But once these three things are established, we say it's constant because it doesn't change. So once we've selected our object and we've selected our surface, the force of kinetic friction is going to be constant from that point forward. And so you can see this in this formula here. Now, we haven't talked about what the symbol is in the middle, that mu sub k, but that's going to be the subject of our next section. But I wanted you to see it here so you could see how straightforward the formula is to calculate kinetic friction. It really just requires us to know the normal force and have this other constant mu sub k here, which is going to be called the coefficient of kinetic friction. Now, you've probably had the experience before where you have tried to, say, push a couch and it didn't move. And that's a separate situation with friction. That's what's called static friction. This is the force that opposes an object that is attempting to slide but does not move. It gets the symbol F sub s. And the thing about static friction is it is not constant. Static friction always counteracts the applied force, and so there is going to be no formula for static friction because it's always going to react to whatever's being applied. And so static friction can cancel out the applied force, but only up to some limit. And so it ranges from 0 newtons to a limit, which we call the maximum static friction. And it's very special and gets the symbol F sub s max, and we're going to deal with it quite a bit in the next section. And this is the force at which the object slides. If the applied force is greater than F sub s max, then static friction can no longer provide enough force to cancel it out, and so we get our object to move. And so F sub s max will have a nice formula, as you can see here, and it also depends on the normal force, the object's composition, and the surface's composition. And so as you can see in this formula here, it also gets a constant mu sub s, which is the coefficient of static friction, and we'll talk about that more in the next section when we talk about coefficients of friction. Now, if you've ever successfully pushed a heavy object and got it to move, then you know it's hard to get it started, but once it starts sliding, it's much easier. And so this tip here says exactly that. Kinetic friction is always less than the maximum static friction. Let's go ahead and look at this in an example. We won't be calculating the kinetic friction by its formula or using the formula to calculate maximum static friction. Instead, we'll just be identifying a few situations and trying to determine whether it's static friction or kinetic friction and how big those forces are. In part A, we see a 3 kilogram block. It has 30 newtons being applied to it, and it doesn't move. So because it doesn't move, this is static friction. And since static friction always balances out the applied force, static friction is 30 newtons. In part B, it's a similar setup. In this case, the force that is applied is 60 newtons. So this is still static friction, and this time static friction changes to be 60 newtons. Again, we can see that static friction is not constant. It really just depends on how much force is applied. In part C, this is going to be kinetic friction because the box is accelerating and therefore moving. Let's draw a free body diagram to help us identify how big that kinetic friction force is. In this case, the force of gravity is the first force we should draw, and it's equal to 29.4 newtons because the mass is 3 kilograms. The normal force is going to exactly balance out gravity, so it's also 29.4 newtons. I'm going to draw the applied force to the right, and I'm going to set it equal to 90 newtons. And I'm going to draw kinetic friction opposing that sliding, so it must go to the left. Now I move on to writing down Newton's second law, and in this case F net equals ma, and I'll choose the positive direction to be the right, so F applied is positive minus F sub k, because it's moving to the left, is equal to, in this case, the mass, which is 3, times the acceleration, which is 10. If we start filling things in, that gives us 90 minus F sub k equals 30, and we find that the kinetic friction is 60 newtons. And that makes sense that there is definitely a large amount of kinetic friction. If there had been no friction in this situation, a 90 Newton force applied to a 3 kilogram block should have caused it to accelerate at 30 meters per second squared. It did not accelerate at that rate. It accelerated at a much lower rate. And so in this case, we can use that information to find that kinetic friction is 60 newtons. And so we can see situations here in terms of calculating static friction and kinetic friction. And the key here that you should take away from this is that static friction is always calculated by balancing out the applied force. There is no formula for it. In the next section, we will be looking at formulas for F sub k and F sub s max, but static friction is really something which you have to interpret based on the applied force.